Okay, good morning. Today I'll record lecture 16 for you guys, and we're gonna start. I'll do the first half. I just want to first half of this lecture spend the time talking about that free radical addition of HCl to alkenes. There were some questions that came up in office hours that were good questions, and I just want to make sure that everyone in general understands what I'm trying to show with these free energy diagrams, and in particular what the problems are in terms of why the HCl addition does not occur. So we'll spend a little bit of time on that. The second half of the lecture will start stereochemistry. Okay, so please remember that we said in the last class, the free radical addition of HCl to alkenes does not proceed. Okay. And the way we explain this, we drew this reaction energy diagram, and it had the different humps and levels. But let me just step back from that specific example and make a couple points, generalizable points about these energy diagrams that there's a fight going on behind me that might be useful for you. So so there are two components that we need to think about. Okay, and so the first component is going to be the overall reaction. So where I start and where I ultimately end up. And that's the what we were talking about specifically was the overall delta H, change in enthalpy for the reaction. Okay. And so this is going to be very generic. So just write starting material, SM for starting material, and then PDT for product. Okay. And yet, if you're good with this diagram, no questions from the last class, you can just skip to part 2 right now. Anyway, let's keep it simple for this discussion. Single step reaction. Okay. I'm going to have some pathway connecting the starting material to product. Okay. And we're going to focus on the delta G term. We limited our discussion to delta H, which is a useful approximation, but in generalizing this, let me just stick with the free energy change. Okay. So the difference in energy between starting materials and products is given by their different heights on the energy diagram. Okay, so that is the change in free energy of the system when I do this reaction. Okay. And the hump that we draw, okay, it's not, there for aesthetics. We draw that hump for a reason. And the reason is that the hump represents, the top of the hump represents the transition state. okay? And also the height of the hump is important, it is meaningful, okay? And this may be one source of confusion, is that, we typically just, if we're not talking about the transition states explicitly, I'll just connect the starting material or product with a point of sort of arbitrary height. But in fact, if we are thinking about the transition states and thinking about their energies, the height of that hump above the starting material energy is the activation energy. Okay, and so this is, I think, that hopefully gets to the crux of the issue. And I hope you believe me when I say that it took me years to get my head around this. So if this is confusing to you, that's okay. These are sort of distinct concepts that we haven't really grappled with. There's no analogy to any other class you've taken. Maybe you covered this a little bit in Gen Chem, but it's not definitely not in this much detail. So the delta G double dagger and the delta G are telling us two different things. Okay, so delta G is a thermodynamic property. Okay. Okay. It tells us overall, does the system, if I run this reaction, does the system increase in free energy or does it decrease in free energy? Okay. So okay. And when the products are lower in energy than the starting materials, we had that the overall delta G is going to be negative. So the delta G equals the free energy of the products minus that of the starting materials. Okay, and so the starting material is greater, you end up with a negative number. And so minus delta G is what we call an exothermic reaction. Positive delta G is endothermic. Okay. And the systems always want to lose energy, right? And so reactions that are exothermic, that give you a negative delta G, will proceed, okay? And so let me just draw those two examples on the next slide to contrast them. So I'll just repeat the diagram here. Okay, so I have two different examples. And in the first example, we can see that the energies of the products are lower than the starting materials, and so the delta G is negative. The reaction is exothermic. Okay. And in the bottom graph, you can see that the free energies of the products are higher than the starting materials, and so the free energy change for the reaction is positive. And we say that the reaction is endothermic. Okay. And so this is the key point. Okay. So what I'm trying to do is, what we need to do to understand the HCl addition is decouple these barriers, these transition states, from the locations of products and starting material and understand them separately, and then we put them together. So the key point in terms of just the energies of the starting materials and products is that a reaction will only proceed if a reaction can only proceed if the energies of the products are lower than that of the starting materials. Okay. And so it was very specific to use can, and I'll explain that relates to the barrier height, which I'll talk about in a second. So in other words, if you're proposing, on paper, a reaction that looks like this one in the bottom, okay, I don't care how much you heat it, how much acid or base you add to the reaction, it's not going to go. Okay. So okay, so these reactions do not proceed. Okay. In the case of the exothermic reaction, again, I'll be very specific. I'll say this reaction may proceed. Okay. And so there's kind of like, there's two analyses that one needs to do. And the first one that we're talking about is what we call the thermodynamic considerations. Okay, so looking at the energies of the starting materials and products, and forgetting about the line that connects them, are you decreasing the energy of the system or increasing the energy of the system? Okay, and if you're decreasing the energy of the system, then you're in good shape, and you can think about the reaction further. If the energy of the system is increasing, the reaction will not proceed. Okay. Again, it doesn't matter how much you heat it, whatever you do to it, the reaction will not go. So I'll write it one more time, and then we'll move to the line. So okay, and so so this is where the barrier, the line connecting the starting materials and products becomes important. Okay, and so the only conclusion that I can draw from this thermodynamic analysis is that this reaction may proceed or is impossible. Okay, if it may proceed, if it's the top case, I know that it's still sort of a possibility. I know nothing about how fast the reaction occurs. Okay, so there are reactions where we will we had just had one in a synthesis that we did where it was a 2-week reaction. It took 2 weeks to get from starting material to product. We've had reactions where, they're done in 5 minutes. You finish adding the reagents and the reaction is completed. And so what we're talking about there are rates of reactions. If my reaction takes 2 weeks or my reaction takes 2 minutes, okay, we can infer that both of those, because they are forming product, both of those are exothermic. The system is losing energy, okay? But the rates at which they turn over and convert to product are very different, okay? And those rates are what we call kinetics, and the kinetics are what comes in with these hump heights, okay? Okay, so on the next slide, let me, we're gonna limit our discussions to reactions that are exothermic, okay, to keep it simple. And let me give you 2 extreme examples of a fast and slow exothermic reaction. Okay, so here are my 2 reactions, right? And I've tried to draw the starting materials at equal levels and the products as well, okay? And without connecting the starting materials to products in any way, you should be able to assess that these are exothermic reactions. And so if we look at the change in free energy, in both cases, it is less than 0. Okay, but now let me give you an example. Let me sort of draw the fast and slow variants of this transformation. Okay, so if this were the 2-week reaction that I was describing, what we would say is that it had a high activation energy. Okay. If this were the 2-minute reaction that I was describing, we would say that it had a low activation energy. Okay, and so let me add some details here. So this is delta G double dagger. We'll call this A, and call this one B, and then this is delta G double dagger B. Okay, and so the delta G double dagger corresponds to the activation energy for a reaction, okay? And the magnitude of delta G double dagger tells me how fast a reaction will occur. And you can't connect, 10K cal delta G double dagger with an explicit rate because you have other factors that come in. But qualitatively, you can say, okay, if it has a large delta G double dagger, that's probably going to be a very slow reaction. If it has a small one, it's going to be a fast reaction. So Okay. And so, so what am I trying to say here? So, so the delta G double dagger gives us a sense for how quickly a reaction may proceed. Okay. And if you want to, you know, what the delta G double dagger is telling us is that I've got to put energy in the system to sort of get over this hump, right? And, you know, why is that the case, right? And so if we think about what the transition states look like, right? Let's consider, so let me just put the question explicitly. So why, you know, why do we need to put energy in to make the reaction proceed? Okay, so why do we need to actually put energy in? Think about, let's go to like something that hopefully you're pretty comfortable with at this point, which is going to be the addition of the protonation of an alkene. Okay, let's just do very simple. So if we have okay, what's going on in that transition state, right? So we just draw it like that, where I just put the proton on there, but there's a transition state linking the two ends, you know, two components on the sides of that reaction. And the transition state probably looks something like this. So you've basically got a partial bond to hydrogen, a partial pi bond, okay? So, the, as you know, so, you know, reactions don't proceed in snapshots, right? There has to be a continuous rearrangement of the system from starting materials to products. And the transition state is sort of the center of that rearrangement, okay? And in this case, I've got partial, you know, partial protonation. The electrons on the pi and the pi bond are reaching towards that proton, okay? Because they're now sort of reaching out to the proton, I've broken a bit of the pi bond, okay? And this is an unstable arrangement, okay? And so this is why they are transition states, are things that the system passes through. It doesn't want to stop there because I don't have full bonding to anything. I don't have a stable arrangement, but I need to go through it because you can't just, you know, jump from one, you know, like I said, you can't do a snapshot jumping from one situation sort of to the next. There has to be a continuous movement of the atoms and the electrons through the reaction pathway, okay? And so the extent of the movement, the extent to which we have to break bonds and sort of do molecular gymnastics to get these reactions to proceed defines the activation energy, okay? And so the take-home message here is that reactions with a very large activation energy proceed slowly, okay? Reactions with a small activation energy are very fast, okay? And those, my friends, are rates. We're talking about kinetics, okay? And so we'll pause in a second. There's two components to these energy diagrams. There's the delta G, which is thermodynamics. Will the system go there? Okay. If it had infinite energy and it was, you know, we had infinite time, could we get there? Okay, that's delta G. If it's exothermic, the answer is yes. If it's endothermic, the answer is no. Okay. The second component of these diagrams are the kinetics, and that's the delta G double dagger. And that's how quickly can we get there, okay? A small delta G double dagger, I can get there very quickly. A large delta G double dagger, it's going to take some time, okay? And so we're gonna, in the next segment, I'll do this for the HCl, the radical addition, but hopefully this is starting to clarify this for some of you. These diagrams are representing two things, kinetics and thermodynamics, and we need to keep that in mind when we're starting to draw these out. All right, so I'm going to pause it and then restart. Okay, we're back. And so let me now return to the HCl addition reaction, and I'm going to leave out the HBr because we don't want to make this overly complicated. I'm going to redraw what I put on the last slide. And for those of you that are looking for the stereochemistry discussion, I think it'll probably happen in about 5 or 7 minutes here. And so what we said in the last class is that you have chloride radical plus the alkene, and that is going to proceed to form an alkyl radical intermediate. Okay. And then that alkyl radical intermediate can react with HCl, do hydrogen atom abstraction, form the product, and regenerate Cl dot. Okay. And we did an analysis of this reaction. Okay. And I'd refer you back to the BDEs that we discussed in the last lecture. But we did an analysis, and we said this first step is downhill by about 27 kcal per mole. Okay. And the second step is uphill by about 7 kcal per mole. Okay. And I just want to say that there's a little bit of an approximation here, which is we're talking about bond enthalpies, delta H's instead of delta G's. Okay. For these types of reactions, delta H's very closely approximate delta G, and it makes it, the discussion is much crisper. We can avoid getting into entropy terms and things like that. So that's an approximation. We're going to assume, delta H pretty close to delta G, and that allows us to use these BDE tables and things like that. So the first step is downhill by 27 kcals per mole. The second step is uphill by 7 kcals per mole. And so let's forget about the humps and the lines for a second. Let's say, what does that tell us? Okay, so the first step is downhill. The reaction will proceed, okay? And so we know nothing about the rate. We haven't said anything about how quickly it will proceed, but what we have said is that, okay, I'm going from a higher energy state where I've got chloride radical plus an alkene to a lower energy state. That's favorable. Assuming the system can get there, we don't know how fast it will get there. We assume it will eventually get there. The reaction will go, okay? The second step, I'm going uphill. Okay, and because I'm moving to a higher energy state, the reaction does not proceed. The system does not want to move to a higher energy arrangement, right? It's like, you know, why would you walk up to the second floor if you could spend your day on the first floor? You just want to stay in the lowest energy arrangement. And this is where the HCl addition, you know, fumbles, is that you can generate these radicals in the center here, okay? That's favorable, but they can't go on because the next sort of the product and the chloride radical that you would form in the next step are higher in energy, okay? And so the system, you get some of this chloride radical, the system gets stuck there, and it winds up, you know, going on to do other things. You can accumulate some of these radicals, they can dimerize, but you don't get this very rapid radical chain reaction that we got in the HBr addition, okay? And I want to wrap this up because I don't want to spend the whole lecture on it, but so this has been a thermodynamic discussion. We're talking about energies of intermediates, of starting materials and products. We haven't said anything about the transition states, okay? And the transition states, again, tell us how quickly the reaction will proceed. And so that energy, the energy of the transition state, is given by delta G double dagger, okay? And it says to us how rapidly a reaction is going to progress to product, okay? And we don't need to, you know, do a detailed analysis for HBr versus HCl because the thermodynamic considerations explain why the reaction doesn't proceed. But for those of you that are interested, the radicals, because they're very high energy, right? You know, chloride is very high up on the energy scale. It raises the energy of the system. The delta G's tend to be quite small. And so what that translates to is fast reactions. And so these reactions proceed very quickly. All right. So I'm going to cut it off here because I need to keep going. But you have it all recorded now. And so I'd encourage you to go back and re-watch this if anything was confusing. And then I will be more than happy to discuss with you on an individual basis. Okay. All right. So so we're going to start the chapter on stereochemistry, okay? And this is this is both a very interesting topic and a very dry topic. And it's interesting from the standpoint of you know, what we're talking about when we talk about stereochemistry are different arrangements of atoms in space, but identical molecules, identical compositions. And so, you know, obviously, like different molecules have different properties. What stereochemistry sort of does is adds another sort of layer of complexity to this, where we say, okay, we've got the same molecules, they have the same molecular formula, but they have different spatial arrangements of atoms. And it turns out that that gives them different properties. So it's not just the composition that is obviously the largest determinant, but then you have how are these things arranged in space. And this is the big, you know, this is the foundation for every single drug, you know, protein interaction. It's the foundation for protein-protein interactions. It's the foundation for catalysis. It's the foundation for, you know, DNA, anything, because the stereochemistry matters. And anyway, so we're going to try and unpack this. And then I say it's dry because we need a way to talk about stereochemistry that's precise and unambiguous. And we're going to have to bring out these old sort of prioritization rules that you know, you just have to learn. So there's hopefully you'll find it very interesting, but then there's also this sort of grunt work that's associated with it. Unfortunately, there's no way around it. So can't apologize for that. All right, so I'm going to start by introducing a few terms, and just so we have them. So stereoisomers are going to be molecules with the same composition and connectivity, but different spatial arrangements in space. So okay, and so a good example of that would be that you've already seen are our friends cis and trans 2-butene. Okay, and these of course have the same molecular formula, right? Same connectivity. If you were to sort of draw everything out, you have the exact same connectivity, but different arrangement of atoms in space, and therefore they are stereoisomers. Okay, and there's an important distinction here, which is that you need to be just a little bit careful about how you apply the term stereoisomer. So for example, if I had the cis arrangement, the staggered arrangement of butane, of ethane, okay, and then I contrasted that with the eclipsed arrangement okay, based on the definition at the top of the slide, you could say maybe these are stereoisomers, right? Because same connectivity, different spatial arrangement of atoms. And strictly speaking, that's true. But we don't regard these as stereoisomers because they can be interconverted by a low energy process. And so in this case, bond rotation about the carbon-carbon bond. And when we covered alkenes, what we said was that for cis and trans 2-butene, you can't interconvert them, at least under any mild conditions, because you have to rotate that central pi bond. And when you do that rotation, you break the 2p orbital overlap. And so those things are stuck where they are. And so it's just a finer point. You have to have some sort of restriction to really have a stereoisomer. And so for conformations like, eclipsed and staggered, where you have this very low barrier to get between them, we don't really regard them as separate stereoisomers, although strictly speaking, they in fact are. Okay. All right. So so a stereocenter is defined as maybe I'll box the important terms here. Stereocenter is going to be any atom where the interchange of two groups generates stereoisomers. So okay, and so for example, the carbon atoms in both of these alkenes are what we call stereocenters. If I exchange or interchange two of the substituents, the terminal hydrogen in the methyl group on any of those carbons, I generate a stereoisomer. I go from cis to trans. And so those are by definition then stereoisomers, okay? Or stereocenters, excuse me. All right, so I want to move to the single most important term of this whole area, which is what's known as an enantiomer, okay? And so enantiomers are defined as stereoisomers that are non-superimposable mirror images of each other. So okay, and so that's a mouthful. So let's unpack that for a second. So for any molecule, I can draw a mirror image of that molecule. And I know this may seem esoteric. Why are we talking about mirror images all of a sudden? But just bear with me for a second. For any molecule, I can draw a mirror image, okay? And the question is that mirror image superimposable on the original molecule or not, okay? And so, for example, if we go back to our cis-2-butene and I draw a mirror plane, right? Reflect through that plane. Of course, it's obvious I can superimpose them. So those are not enantiomers. They're the same molecule, okay? But where it gets different and why this is so important is that because carbon can bear 4 ligands, you can generate enantiomers very quickly with a single carbon center. And so this is, let me give you an example. So tetrahedral carbon will form enantiomers. And let's just do like an example here. So if I have this molecule, okay, and so I've drawn that flat intentionally, but we know that carbon is not flat. We know that carbon is tetrahedral, sp3 hybridized. And so if I really want to talk about this molecule more accurately, I need to use the line wedge notation. And so let me just want to back into this slowly. So I'll draw it as a tetrahedron, and then I need to pencil in the substituents. And the question is, where do the substituents go? And the drawing on the left gives me no indication of where I should put anything. So it's arbitrary. So what I'll do is I'll put the OH up here just so it looks close, put the H here, put the SH here, and then the F back there, okay? And so if I gave you the structure on the left and you drew the structure on the right, that would be a more accurate description, but it's still incomplete. And the reason is that this molecule possesses a non-superimposable mirror image, okay? And so let's suppose that I interconvert the positions of the fluoride and the thiol. So now the thiol is back and the F is coming forward, okay? Those two molecules should look a little different to you. The configuration at the carbon center is different, okay? And if you allow me to flip this molecule or rotate around the CO bond 180 degrees, what I end up with is a drawing like that. Okay, so I haven't changed anything in the molecule, just rotated about the CO bond. And if I redraw this top molecule, okay, no changes there, just redraw it exactly as I did. Hopefully you can see that they are mirror images of each other. Okay, and what you want to do is convince yourself that they're non-superimposable mirror images. Okay, and so to do that, let me see if I can go to Spartan here without getting into trouble. Okay, so I drew those molecules in Spartan, and so here's the OH. This is the fluorine here, and yellow is sulfur, and then H is the hydrogen that's attached to the carbon. So this is one enantiomer, okay? And maybe, let's see, put it, that was sort of how we oriented it initially, okay? So fluorine's going back. Over here, I've got the other enantiomer, okay? And so I put my alcohol up. Now my fluorine's coming out at me, my sulfur's going back, okay? So I've changed, the only thing that's changed is the configuration of the carbon, okay? What I can do is I can overlay these, or attempt to at least, all right? Let me just align this real quick. I can attempt to overlay these, and no matter what I do, I can't get everything to line up. Okay, so if I line up here, I'm lining up the OH group and the fluorine, but if I then rotate, you can see that the hydrogen and the sulfur are not lining up. And so, you know, we can play the game then where we line up the hydrogen and the sulfur like that. And let me just realign this. Sort of a little bit out of alignment, but you get the idea. I line up the hydrogen and the sulfur there, and now if you look at where the oxygen and the fluorine are going, they're not lined up with each other. Okay, let me just see if I can get that on top of each other. See if that helps. If not, I'll yeah, perfect. So you can see it. So these are the two molecules on top of each other with the sulfurs and the hydrogens lined up, and you can see that the fluorines and the oxygens are not correctly aligned. So there's one, there's the other, there's the superposition. So the point is that no matter what I do, I can't align these two molecules, can't superimpose them. And that is the definition of an enantiomer. So let me go back here, go back to the whiteboard. I'm pretty sure I lost everything. Yes, I did. Okay, so Enantiomers are isomers that are non-superposable mirror images of one another. The other example that people often use is the hand. I think it's easier to use gloves because I can hold them. You know, here's one glove, here's the other glove. You can try and put these on top of each other. You can't get them to perfectly superimpose no matter what you do. The gloves are, in fact, chiral, okay? And this is an important point, which the gloves do a nice job of representing, which is that enantiomers have identical physical properties, okay? So okay. And so going back to the gloves, if I weighed this glove, it would weigh the same as this glove, right? These two gloves are the same color, they have the same pattern, right? They all have 4 fingers and a thumb. They have the wrist, they're identical, okay? It's the same thing for enantiomers. Same boiling point, same melting point, same NMR spectrum. We'll get to NMR spectroscopy. Same spectroscopic properties with the exception of one in general, okay? Same properties, okay? So enantiomers can't really be distinguished by any sort of physical property, you know, looking at differences in melting points and things like that. I just closed with 2 more that you're familiar with, maybe. So this is a very popular molecule. So this is known as R-carbone. And the R refers to the configuration here, which that's the sort of the dry part of this chapter that we need to work through, which we'll do in the next lecture. But that molecule, my friends, is spearmint. So when you smell spearmint, you're actually smelling that molecule. And it has an enantiomer, okay, because it has a chiral center. And we'll talk about that when we get to, I want to save that one for diastereomers for an important reason. But the point is enantiomers are everywhere because carbon can contain 4 ligands, and it's more often than not those ligands are different. And so this is a property that is unique to organic chemistry. And so it takes some time, I think, to get your head around it, but it is absolutely very significant. So, all right, so I'll stop there. And Monday, we're going to pick up with, we'll pick up with the nomenclature, which I know is going to be a slog, but we'll get through it. All right, guys, talk to you later.